All right, we started section 10.6, albeit a very short section, and just barely started it last time. We talked about how our different conics can be related by this ratio of a distance from a point on the curve, a point in the plane, to the directrix, and a point to the focus. And if that ratio is called the eccentricity. If the eccentricity is between 0 and 1, it's an ellipse. If it's equal to 1, it's a parabola, and if it's greater than 1, it's a hyperbola. And I gave you the homework at the bottom, even though we can't do any of it yet. Okay, so Theorem 1017 is where we're going next. And this one actually talks about how we will create our equations based on those kinds of pieces of information. Also, this is different than what your book does, just so you know. This is what I used when I did the other book, and I liked it a lot better. So when you're looking at and comparing this, don't be freaking out and being like, this isn't what's in there. What's in there is fine. It just puts all of the formulas into one pot, and I think this separation of them out actually makes it easier. So let me show you what I'm talking about. So this is Theorem 1017, and it says the following. It's Polar Equations of Conics to start with. The conic with eccentricity e greater than 0, and we're going to only do it for the focus at the center, at the origin. So in focus 0, 0. Excuse me. And the indicated directrix has polar equations, or polar equation. These are multiple options. So R equals ED over E cosine theta plus 1.
Is it supposed to be the other way around? Sorry.
It's supposed to be the other way around.
1 plus E cosine.
It doesn't matter.
Okay.
It shouldn't matter. Your book does it the other way around, but you'll see in a minute why I've got it written this way. For directrix, x equals d, and d is positive. You have almost the same equation on the next one. It will differ because it will say minus 1 on bottom. So ed over e cosine theta minus 1. And it's for the same kind of directrix. That is to say, it's x equal d, but the difference is that d is negative. Okay, so if these are your directrix, you're looking at vertical directrix, right? One would be on the right-hand side of the graph, and the second one would be on the left-hand side. Yes? Yes, I left E off. No wonder it looked a little bit off center. Thank you. Yeah, it should be the same on bottom except for the sign. The third and fourth ones here mirror the first and second ones, but instead of having cosine, they have sine. So it's ED over E sine theta plus 1. And these are for directrix that are horizontal. So for directrix, y equals d, where d is positive. And then, of course, it'll be the same thing for d negative on number 4. So r equals ed over e sine theta minus 1. For directrix, y equals d, and d is negative. So just kind of throwing it out there where this is coming from. It didn't just appear out of nowhere, of course, but to give you a kind of a sense of where it's coming from. Each of these is derived from the square root of x squared plus y squared equals e times d minus x, along with a change of variables into polar. Coordinates.
And these are just for eccentricity greater than 0.
Yes, eccentricities are always greater than 0
Oh,
because they're ratios of distances, and distances are always
I was
positive.
thinking 1%.
Oh,
Good now.
yeah, just for greater than 0.
My brain was not working.
It's okay. Okay, and what I have remaining for us after these is example problems. I think it's 3 example problems of how we can use this information. So here's our first one. We're going to find the eccentricity and distance from the pole to the directrix of the conic.
Since most of these are at focus and center,
Mm-hmm.
so we already know that the directrix is basically going to be the distance itself.
True. Yeah. Directrix of the conic. Hang on just a second. Let me finish writing this in. We're going to also sketch and identify the graph. So I'll say ID and sketch the graph. So our first equation that we're given is r equals 6 over 2 plus cosine theta. And this feels a lot like when we were working with our geometric series in our last section, and we were trying to change them into that a over 1 minus r formula. So in particular, we were trying to get a 1 at the beginning. Do you guys remember that? And so we were manipulating an equation to match something else, and that's what we're doing here too. We're manipulating this equation to match one of the 4 forms that we had on the previous theorem, okay? So if you're taking a look at this and you're trying to get it to match one of those 4 forms, which of the 4 forms is it going to match? It's going to match number 1. Yeah, because it's got cosine in it and there's addition. So we're going to get it to match the first one. And if you take a look at this, as you're seeing through what's happening, we need for the number at the end, instead of the number at the beginning, right, like when we're working with geometric, to be a 1. So when we're taking a look at this one, I know that the 2 is written at the beginning. It doesn't really matter where it's written, right, because like Ethan was mentioning before, like, can we put 1 plus at the front? Well, of course. We need that to be a 1. So what would we have to do to manipulate this to actually look closer to the form that's on the previous slide? Yeah, we're going to divide everything by 2, right? So if I change this, actually I'll put it over here. I can divide everything by 2, so I have 3, and then I have 1 plus, and it would be 1/2 cosine of theta. Once it's in that form, it's easy to identify the other pieces of information. In particular, what is E? It's 1/2. And because E is 1/2, I actually know what kind of conic it is as well. That's the previous day's work that we did last Friday. What kind of conic do we have if E is 1/2? It's an ellipse. So I know I have an ellipse. What else did I need? D, I guess, right? The directrix. So what is the D value according to our formula here, what our equation rather that we were working with? Yeah, it's 6. So our directrix, that's what D is, but the directrix itself then is what? Yeah, it's x equals 6 because we have the first type of formula, or first type of equation, excuse me, from the previous slide. Okay, and the last thing I think that it told me to do was to sketch, right? We found the eccentricity, we found the distance, we identified that it's an ellipse, and we need to sketch the graph. So we're ready to sketch a graph. The directrix should be pretty straightforward to draw. Where are we drawing that in our on our graph? Yeah, it's at 6, right? Let me see if I can get my grid. Make it easier to draw. Okay, so x equals 6. Roughly. There's my directrix. Let me see, what else do we know? What else can we draw in? Okay, I was trying to decide how much of this I want to go into depth on and how much we're going to use our calculator for. Okay, let's use our calculator for the rest of it. I think that's all I intended for us to put on here. I didn't write a lot of notes to myself. So grab your calculator. I have mine with me. I do. Oh, and last time when I was having trouble getting my area formula to work, some of you were still here when I figured out what I had done. I don't know who was and wasn't here. But when I was finding the function integration, that math 9 button, I put in Y1 instead of R1. That was why it was freaking out and not giving us the right values. Because we're using polar, I should have used R1 as my equation instead of Y1. So, all right, let's see here. So we have either version of this will be fine to enter in, of course.
We're trying to integrate 0.
Huh?
We're trying to integrate 0. Nothing.
Last time?
Yeah. Because C constant.
We were trying to integrate what I had stored in Y1, and the Y1 was in a different screen in my calculator, so I actually had something in my Y1, so it was giving me values, but yeah, if you didn't have anything in there, it would have given you an error too. Window, so 0 to 2 pi should be right, and if we look from, I had my window set at -5 to 5, it's a little bit small.
I find that sometimes it's best to like have a negative in the window.
Mm-hmm.
You know, from 0 to 2 pi, like -pi.
It can be, yeah, it can be very helpful. I am seeing a x-intercept at 2, and then another one at 6. Is that what you guys have on your screens?
What does the directrix mean?
What does it, what?
It's like an anti-focus.
It's measuring a distance. So the eccentricity is measuring this ratio of distances. And so the distance, I'll draw it in a picture here in just a second, and then you'll see where it is. Okay, let me show you from a picture form. Your book actually does a really nice job of showing some pictures about that. 1, 2, 3. Let me try and get a picture here that's reasonable.
My theta step's really low.
Okay, mine looks about like that on my screen, approximately. So if our focus, here, our center would be here. And so our focus is approximately, from a graphical standpoint, in here and over in here. So if I were to take a point on my curve, any point will work. So let's just take this one right here. And I were to calculate the distance from that point to, I want a line. If I were calculating the distance from that point to the focus compared to that point to the directrix, my ratio is actually going to be, well, in this case, 1/2 specifically, but less than 1 is the idea. All right, and that's what gives me the ellipse. If that ratio ends up being greater than 1, I would have a hyperbola, and if it's equal to 1, I have a parabola. So really nicely like in a parabola, and you guys know that I told you I wasn't going to be an artist. No, that wasn't me, but I could have said that in our math club meeting today. But if we had a parabola, and this is probably going to be not convincing at all, but we'll try it anyway. If we had a parabola, say, and we had our directrix right here, and our focus, that was awful, that's not even a horizontal line, but so here would be our focus because it's centered evenly around them, right? Then every point on my parabola, wow, that was a highlighter. Every point on my parabola is equal distances. I told you this is not going to be good. That's a little bit more convincing. Equal distance back to the focus as it is to the directrix. Okay, so the distances are equal on a parabola. On a hyperbola, the distance is going to be actually further away from the directrix than it is, did I get that right? Which way is it set up on your equation? Yeah, then the focus, and then on the ellipse is the one that I already drew. Okay, so that's where the eccentricities come, the ratios. Okay, from any point on your curve.
It's equal distance anywhere on the parabola?
Yes, if you measure from the parabola, again, my picture, don't take my picture as it's just a sketch, right? It's really terrible. But if I were to take a real graph with a real parabola and I were to take this distance here, it would be the same as this distance here, and that would work for any point on my parabola. Okay, and again, you're looking at, I mean, from point to point, that's easy, but when you're going back to the line, it has to be a perpendicular distance, of course, to make that work. Yeah, that'll work for a parabola. It won't work for the ellipse and the hyperbola. It'll either be greater than 1 or it'll be less than 1, and depending on which one you're looking at.
Even when it's, okay.
Okay. All right. We're going to flip around what we're doing and start with some information. That's not the one I want. That's the one I want. Start with some information and we're going to create the equation. Okay, so that's the last two examples that we're going to do, is we're going to start with information that is given. So we're going to find, find the polar equation for the conic with focus at the pole. Okay, and our second example is that we're going to have a directrix. Let's spell that right. Of x equal to 2, eccentricity of 1.2. Yeah, and it doesn't ask us to sketch on this one. So, all right, can you tell me what the equation is going to be? Just by that information. Your book's actually going to tell you. I don't know why it does, but.
Well, D's positive, so, and we're dealing with x, so we're dealing with number 1, I think.
Okay, you're answering a different question, and we'll get to that in a minute. But what's the shape of my conic? Hyperbola, parabola, or ellipse? It's a hyperbola. How do you know, Shayna? Yeah, because the eccentricity is greater than 1. And like I said, your books actually tells you on these. I don't know why, because you certainly should be able to see that. But yeah. And then you're actually trying to decide for me, Ethan, which was my second question, which of these equations that I'm going to be using. So my directrix is an x equals, which puts me either in case 1 or case 2. And the directrix is a value. The d value is positive, right? So it is case 1. So you're right, yeah. So eccentricity is 1.2. Excuse me. So R equals, and so my eccentricity is 1.2 over 1.2 cosine theta plus 1. And then the d value is 2, right?
Is it supposed to be ED on top?
Yeah, I'm going to I haven't finished it, yeah. So the eccentricity is 2, so I have that one as a 2. You're right, on top. So my equation ends up being, when I'm done, 2.4. And then I have 1.2 cosine theta plus 1. Make sense? Yes. Why? Okay, we're going to do one more. Same directions. Actually, maybe I have space on this previous slide. Sure, why not? Let me just move these around. Okay, number 3. Directrix x equal -2 equal 1.
So is this case?
Okay, so we are in case number 2, if you will. From the last theorem, this was case 1. Are we dealing with a hyperbola, parabola, or ellipse?
Parabola.
This one's a parabola. Good job. And what would my equation be for this?
Case, well, you wrote it, case 2.
Mm-hmm. And so what will it be when I fill in the details for it?
-2 over cosine theta minus,
Yeah, minus 1.
Yeah, -2 over cosine theta minus 1. And could we graph this if we needed to? Sure, absolutely. We've got a calculator, right? And just a reminder from last time, I'll copy and paste it here. I promise I'll bring back my slide just a second.
Did you explain again how you're choosing between the cases? I understand when you're looking at like x equals, you're looking at the direct x and based off of x or y equals.
Yes. You're looking at which case you're in by the directrix. In both of the examples I just gave, we had x equal equations. And then the d value being positive or negative.
Oh.
Yeah, so the first one was positive, so we're in case 1. The second one, the d value is negative.